Unit 4, Development of the Modern Atomic Model. The model of the atom previously, so what Niels Bohr had actually proposed, it didn't provide an adequate explanation about the behavior of electrons. Now, as I mentioned before, when we look at the atom, the parts of it, in other words, the subatomic particles, are so small that you can't observe them directly. So we only can observe them indirectly. And scientists make prediction that if those subatomic particles act in a particular way, we should see, or we should be able to observe certain phenomenon. And so when we look at this, one of the things they observed was that when when electrical charge was passed through a low pressure gas, it emitted colored lights, which when passed through a prism was split into line spectrum that was unique for each element. Each line was of a different color and therefore of a different frequency and energies. The present model of the nucleus could not reliably explain these spectral lines. So it was concluded that the electron moved in an orbit. Each would have specific energies. Orbits further away from the nucleus having more energy than those closer to the nucleus. Also, as energy was absorbed by the atom, electrons move to high energy levels called excited state, and then immediately fall back down to originating level called the ground state. So let me explain this by looking. The previous model of the atom could not explain this phenomenon that was observed. So, like what I said was that you can't observe the electrons of the atom directly, but what you can do is you can observe how the atom interacts with the environment, and we can make certain assumptions that if its composition is, let's say, electrons in energy shells, that you'll have a certain behavior. And this is contrary to what we had understood in the past. So since electrons and light have some similarities, the development of the modern model of the atom corresponded with the development of a modern understanding of light. Light, which is a form of electromagnetic radiation, also exhibits some properties of particles. Okay, so light has both wave-like and particle-like properties. So it was concluded that electrons moved in an orbit, each of which have a specific energies. Orbits further away from the nucleus have more energy than those closer to the nucleus. As energy was absorbed by the atom, electrons move to high energy levels called the excited state and then immediately fall back to the originating level called the ground state. So that's what I showed previously. Since electrons and light have some similarities, the development of the modern model of the atom corresponded with the development of the modern understanding of light. Light, which is a form of electromagnetic radiation, also exhibits some properties of particles. Electrons, which we have seen are negatively charged subatomic particles, have some wave-like properties. So if we look at the wave theory of light, it could not explain the photoelectric effect. So if we look at the photoelectric effect, that's when, which is the emission of electrons by some metals when light shines on them. The wave theory could explain electrons being knocked from the metal surfaces, but not why only certain frequencies of light caused the photoelectric effect. Also, the fact that when a metal, such as iron, is heated, glows with a white color when very hot, but the wave theory predicts that it will emit primarily ultraviolet light. So both of them, the development of our understanding of the electron as well as the properties of light, our understanding of light, they were related and they occurred they they are understood and developed at the same time. So in 1900, Max Planck proposed that when a hot object loses energy, it did not do so continuously, as would be expected if light were a wave, but happened in small packets of energy called quanta. So with quantum, it's a finite quantity of energy that can be gained or lost in an atom. And a photon is a quantum of light. So Planck proposed the following relationship between quantum of energy and the frequency of energy. And I'm this formula, which uses Planck's constant, you're not going to have to do anything with this. I'm showing this because I just want to, I guess, illustrate it so we have a better understanding of light. Okay, so looking at this picture on the second page. So if you look, this is showing you the different states. So if you look at the atom, these are different levels, if you will, energy levels that you would be able to find electrons. So we have one. So if you can see over here, this is one level. This is another level. This is another level, and another level. And you can see that these levels are they're consecutive and they go further away from the nucleus. And what I'm showing here, so let's take a look at this here. Okay, what I'm showing there is that electrons can move from a lower energy state. So what we mean by that is that the electrons move from this lower level to a higher level. Okay, and that's what I'm showing here with the arrow moving up to a higher energy state and then moving back down. Now, why does that happen? Well, if energy is absorbed by the electron, that electron will then move up to a higher energy state, and then immediately, and that's called the excited state, immediately wants to fall back down to the ground state. When it does that, it releases energy. And we would observe that as potentially light, depending on the frequency. So let me draw a line here like this. If you have, let's say this is the ground state right here. If an electron is here, if energy is absorbed by the electron, it will immediately go to a higher energy state, and that's called its electric state. The excited state. So this is the ground state, and this is the excited state. Okay? Now, electrons don't want to stay in an excited state. What they want to do is they want to go back to where they came from. So what's going to happen is that as soon as it goes to the excited state, it's going to go back to where it came from, which is the ground state. But it has all the energy that it absorbed when it was in the excited state. So it falls back down, but the energy has to go somewhere. So absorb energy to go to the excited state. When it falls back down, it has to release the energy. And the energy is going to be, in some cases, observable light. Okay? And now this can also be observed if you heat up a piece of metal with enough heat, and especially if it's in a dark environment, you would see the metal is glowing. The metal is glowing. Why? Because heat is energy. And that heat is absorbed by the electrons, which move to an excited state and then fall back down to the ground state, and they release light as energy. Okay? Now, each atom of an element has a specific line spectra. In other words, if you were to, let's say, put a gas like neon or another gas, another element like sodium into a tube, it's in a gas state, you pass electrical and electricity through it, it will cause electrons to move from ground states to excited states. And when that happens, they'll fall back to the ground state and they release light. Each element will produce a certain line spectra. And what that means is that you would have a bunch of different colors that were produced by each element. And it acts as a fingerprint because each element will produce different colors, and that depends on the number of electrons they have and the electron configuration, and how high the electrons move from lower energy states to higher energy states. And that's actually when scientists say that they can determine the composition of stars that are literally millions of light years away, they could determine the composition because the color that they actually produce is a result of the line spectra of the gases that they are composed of. So they can determine what it is. Okay? So if we look at the previous model of the atom, I'm going to go back to this drawing for a second. If we go back and look at, well, what is it that we're saying? Well, the takeaway from this is that what you should know is that when energy is absorbed by an atom, that causes the electrons to absorb energy. The energy is absorbed by the electrons causes them to move from a lower energy state to a higher energy state. So let's see, this is an electron here. It absorbs energy. So let's say this is energy. That energy, which is absorbed by that electron, that causes that electron to move from its ground state, which is right here, to the excited state. Okay? So the electron here has less energy than here. Where the energy come from? So you'd have energy absorbed by the atom. Some energy is absorbed by this electron. This energy that the electron absorbed causes it to move from its ground state to its excited state. But then it wants to fall back down again. So the electron is going to fall back down to its ground state. When it does that, it's going to release the energy that it absorbed. And we could experience that as light, right? Visible light. It could be heat. Okay? So it could absorb as ultraviolet light or other frequencies that we're not capable of observing without using equipment. So it could be like radiation, other forms of radiation that are not visible to light. I'm sorry, not visible to our eyes. Okay? And also, we should be aware that each element will produce a line spectra. What does that mean? If a certain amount of energy is passed through a gas composed of a particular element, it will produce light of different frequencies, and that the frequencies of light that are produced by that specific element acts as a fingerprint for that specific element. Okay? And what I did down here on the bottom of the page, so if we observe hydrogen atoms, electrons in the diagram above, so I'm explaining this here, we can see that the electrons at the ground state N1, so down here N1, has energy of negative 13.6 electron volts. And that when 10 electron volts of energy absorbed, it will move to the N2. In other words, it goes from here to here, from the first energy state to the second energy state, which is the excited state. It does not stay in this energy level, but immediately falls back down to the ground state, emitting light of the same energy value, 10.2 electron volts. It's not going to emit less. It's not going to emit more. Excuse me. It's always going to emit the same amount of energy that was absorbed. Other electrons also illustrate this. Electrons absorb energy moving from the ground state to the excited state and then fall back down to the ground state, emitting energy of equal value that they absorbed. Also, the magnitude of the energy absorbed, right? So in other words, if you have more or a great amount of energy absorbed, the higher the frequency of light that is emitted. It might be apparent from the diagram above that electrons never move to an excited state that is in between the energy levels. This pointed to the fact that electrons can only occupy specific energy levels around the nucleus. So you're never going to see an electron moving to it in between the energy states. Okay, so if I go back to this diagram, here, let me take this space and show it. Okay, so if this is the first energy level, n equals 1. Let's say this is the second energy level, n equals 2. The electron will move from the first energy level, n equals 1, to the second, and fall back down to the first. It's not going to go in between. So if this electron here, it's not going to move in between it, like to here, and fall back down. That's not going to happen. It's always going to go from one energy state to another. It could jump up 2. Let's say this is n equals 3. Okay, an electron could move from this first energy state all the way up back to the n equals 3 and then fall back down. If it does that, because that's more energy, it takes more energy for it to go up to here, it's going to release more energy when it falls back down. This would be a higher frequency light. Okay, and we would see that as a visible light that would actually be a different color, or it could actually be, if it's enough energy, it could be ultraviolet light, which is much higher frequency, or it's a high frequency and has more energy than visible light. Now, this just shows you the Balmer-Rydberg equation. You don't need to know this equation. I just wanted to illustrate or show you that you can calculate out the different frequencies. And I guess one thing to keep in mind is that if you look at the frequency of the light, it is going to correspond with a color. So the shorter the frequency, the higher the energy is. So if you look, light going from the N6 to the N2, so you're going from the 6th energy level to the 2nd energy level, you're going to produce light with the frequency of 410 nanometers, which is magenta. This is a higher frequency. In other words, this has much more energy than if you go just from the N3 to the N2. So in other words, it's falling from the N3 to the N2. When it does so, it's going to release light that is 656 nanometers, which is red. Okay, let's go back up here. So this one here, the N6 to N2, what that's saying is that an excited electron has moved all the way up from the N to the N6. When it falls back from the N6 back to its ground state, which is the N2, it's going to release light at a frequency of 410 nanometers, which is magenta. That is a higher frequency. The shorter the wavelength, so this is 410 nanometers, the higher the frequency. The longer the wavelength, the lower the frequency, the less energy that it has. The shorter the frequency, the shorter the wavelength, the higher the frequency, the more energy it's going to have. All right, that's the takeaway from this. You don't need to know the Balmer-Rydberg equation and do calculations from it. You just need to know that the more energy that the electron has or releases when it falls from the excited state to the ground state, the higher the frequency, the more energy it has. All right. Now, some more definitions. Quantum. Quantum numbers, these are numbers that specify the properties of atomic orbitals and their electrons. So what we're going to talk about now is how electrons are arranged around the nucleus of an atom. Everything we've been talking about is leading to this. And for the tests, this is really the part that you'll be responsible for in this unit, in the second test that's covering this unit. So the quantum numbers describe the properties of electrons in atomic orbitals. So you have the principal quantum number, right? That's symbolized by N, which indicates the main energy levels surrounding a nucleus. There are 7 consecutive principal quantum numbers, right? Number 1, which is the closest to the nucleus, to 7, which is the furthest away from the nucleus. The higher the principal quantum number, the more energy the electrons have that occupy them. And as you saw, electrons can move. They can move from one energy state to another. So they can move from lower to higher, but they fall back down to the ground state and release energy that they had absorbed. Orbital quantum number indicates the shape of the orbital. So orbital shapes, they're designated by letters. So you have S, P, D, and F. S is easy. S looks like a sphere. So what does this mean? Let's say this is the nucleus. If we can predict, we don't know exactly where, but we can predict where the electrons are around the nucleus of an atom. But again, we don't know exactly where it is. So I'm going to put a little P here to indicate the nucleus. And so the S orbital, which is the spherical orbital around the nucleus, this is the location where an electron could be located, or 2 electrons. But we do not know exactly where they are. So if you look at a diagram of the S orbital, what you'll sometimes see is it's represented like this, where you'll see dots like this. Okay, and what you notice is that as I move further away from the nucleus, the concentration of dots is less. That doesn't mean that there's a whole bunch of electrons. The dots that I'm showing here are where you have the potential, theoretically, of finding that electron, but we can find it more frequently closer to the nucleus than further away from the nucleus in this little sphere. So this is your S orbital. And this orbital, again, it predicts where you would find the electrons or electron of an atom. The P orbital will hold a maximum of 2 electrons. But again, you don't know where they are precisely in this area. You just know they're here. They're more frequently closer to the nucleus than they are further away. So the further away you get, the less frequently you're going to find them there. Now the P orbital is dumbbell shaped. And so again, this is, we're just predicting where you would find it. So if I look at let me draw the nucleus again. So I'm going to use N for the nucleus. What you would see in the p orbital is that it looks kind of like this. So you could find electron here, here, and they're different. They're going to actually be spinning in different orientation as well. Okay, so you can find them around here, and so they can be found somewhere within this spot. That again, it looks like a dumbbell. Okay. Now, if you look at the D, it has 4 lobes, so it looks similar, kind of like this. So you can find the electron somewhere within these. Okay. Okay, and then, but if you look at the F, it's really complex. And if we look at where do we find these different suborbitals within which of the orbitals? So the shape, the letter represents the shape of it. Within the first principal quantum number 1, you'll find one s orbital. But if you look at the second principal quantum number, you'll find 2 suborbitals, an s and a p. And then the third one, you'll find sp and d. The fourth one, you'll find sp, d, and f, right? Fifth one, you find SPD and F, SPDF in the 6th, and SPDF in the 7th. Now so if you look at the S suborbital, so the S will hold a maximum of 2 electrons. The P will hold a maximum of 6 electrons. The D will hold a maximum of 10 electrons, and the F will have a maximum of 14 electrons. All right. The magnetic, so I'm over here. The magnetic quantum number indicates the orientation of an orbital about the nucleus. So the S has 1 possible orbital. The P has 3 different orientations. So if you were to look at we said that the P has a dumbbell shaped. So if this is the nucleus, what you would find is that it kind of looks like this. You have 3 of these dumbbells, and each end of these will hold an electron. That's where we get the 6. And actually, these electrons are spinning in opposite directions. So if I look at these opposite of each other, this electron would be spinning, let's say it's spinning counterclockwise, and this one here is spinning clockwise. They're never going to spin in the same direction. So so let's look at this. Spin quantum number has only 2 possible values, plus 1/2 or minus 1/2. This indicates 2 possible states of electron. In other words, electrons spin in opposite directions. Okay, magnetism is interesting to note that all magnetic phenomena stem from the motion of electrons about the nucleus of the atom. So the direction that they actually spin will determine magnetism of an atom. So electron configuration itself. So electron configuration is the arrangement of electrons around the nucleus of the atom. So the rules governing electron configuration. Aufbau principle. An electron occupies the lowest energy orbital that it can receive it. Hund's rule. Orbitals of equal energy are each occupied by one electron before any one orbital is occupied by a second electron, and all electrons in singly occupied orbitals must have the same spin. And then Pauli exclusion principle. No two electrons in the same atom can have the same set of four electron quantum numbers. So what does this all mean? Okay, let's look at, well, how are electrons and electron configuration represented, because there's ways that we can represent it. We can use orbital notation. We can do electron configuration notation, and we can do electron dot notation. All right. I think it's helpful to first start with orbital notation. So I'm going to do a couple here, and then actually let's go to the next page and I'll show you. Go back to here. So electron configuration notation. Sorry, I want to do orbital notation first. Let's do orbital notation first. So orbital notation uses these arrows to represent the electrons, which is shorthand, is used in this electron configuration notation. And what you simply represent here, let's say you have hydrogen, and let me go back, and I'm gonna represent the same atoms that we just did, but using electron configuration notation. Configuration notation. Now, the electron dot notation is the easiest one. All you do is put in there the valence electrons. All right. So how do I know the valence electrons? So in the main group elements, you would just use the group number that you would have. All right. So if the atom is found in the and let's all right. So let's start with something really easy. Hydrogen. Hydrogen has one proton. So in the neutral atom of hydrogen, it has one proton and one electron. So if we represent the hydrogen, I'm going to put a little p, that's its nucleus. Okay, it will have one electron, right? That's in the s orbital. I would represent it in electron configuration notation. Okay, so let's do orbital notation first. All right, you're going to use a little line like this, and I'm going to put under it, the orbit that is. So 1s. Now hydrogen has one proton and one electron, and we want to represent the electron. So I'm going to put an arrow like this. All right. So that arrow represents that one electron that it has. So this would be the orbital notation for hydrogen. Okay. Now, if we look at lithium, lithium is the second element. Oh, sorry, the third element. So lithium has 3 protons and it has 3 electrons. Okay, and then let's look at helium as well. Helium, it has 2 protons and 2 electrons. I mean, ignoring the neutrons. So if we did the orbital notation for hydrogen and helium and lithium, they would look like this. So I'm going to go back up here to this table. This diagram that I wrote here, this shows you the order in which you add electrons. So I'm going to add electrons first to the 1s. And these arrows here represent the direction that I'm actually adding them. So helium, I'm going to draw again the line like this, and I'm going to write 1s under it. So if I look at this diagram up here, 1s is the first one that I fill. So I'm going to put one arrow here like this, and we know that you have to have the electrons spinning in opposite directions. The direction the arrow actually represents the spin electron. So I have one going up and then one going down, and that's representing two electrons, and they're spinning in opposite directions. And now, if we look at lithium, lithium has, if it's neutral, 3 protons and 3 electrons. So I'm gonna put 1s, all right, and it's 2 electrons in the 1s, but that's full now. I only can fit 2 electrons in the 1s. So I'm gonna go back up here to this diagram, and you can see that the next level, the next one I fill is 2s. So I'm gonna put another line here, 2s, and I only have to add one more electron. So I'm gonna put an arrow like that. Okay. So that's representing 3 electrons that the lithium has. One's in the 2 in the 2s, 2 are in the 1s, and 1 is in the 2s. So how about if we start adding more electrons? So if we look at larger elements, okay, what I'm going to do is let's look at carbon, oxygen, and then finally we'll look at phosphorus. So carbon, it has 6 protons. So if it's neutral, it's going to have 6 electrons. I'm going to put a little N here to represent the nucleus of it, right? And we have 2 electrons in its first energy level. And then if you look, it's going to have 1, 2, 3, 4, and the next one. Okay? So we're gonna represent this using orbital notation. So if we go back up to this diagram here at the top of the page, I'm going to look at that and say, well, where do I put those first 2 electrons that it has? So we start here at the 1s. Okay, so we're here at the 1s. So I'm going to put this here. I'm going to put 1s under it. And there are 2 electrons I'm going to add to it. I have to put the arrows in opposite directions because it shows the spin is different. So I'm accounting for 2 of the 6 electrons that carbon has. I need to put 4 more in there. So the 1s is full because we said before the s can only hold a maximum of 2 electrons. So I'm going to go back up to the top of the page and look at that diagram that I made showing the order of electron filling. And I'm going to see here, the next one, I'm going to go and fill the 2s. So 2s, 1 electron, right? Second electron. Try that again. So 1 electron, my second electron. So now, right now, if I look, I have 4 electrons. We said that carbon has 6 electrons, so I need to add 2 more. So I fill the 2s. I need to go back up here again. So I look, there's no more left in this second row. So I'm going to go here to the next one. So that's showing that I'm going to have to go to the 2p. So if you look, I'm showing an arrow. That's showing the direction that I fill it. So my 2p is going to be the next one I'm going to fill. So 2p. Now we said that p will hold a maximum of 6 electrons So I actually have 2p. I'm going to put 3 times 2p and 2p. And oftentimes it's represented like this. You'll see 2px, 2py, and 2pz because they're different orientations. So the 2px is at the x-axis, 2py is represented at the y-axis, and then the 2pz it goes in between it. So I'm going to put 1 electron in this 2px. Now, in order for me to fill the 2px again, I'd have to put at least 1 other electron in the 2py and the 2pz. So I can't do that because I don't have enough electrons. So I'm going to actually have to put 1 in the 2py. Okay? So now I have 2, 4, 6 electrons represented. So if you look at it, the 1s, we have 2 electrons in there. The arrows are opposite spins, so they're opposite directions. The 2s I filled with 2 electrons. Both electrons have opposite spins, so the arrow's going up and down. And then the 2px, I put 1 electron in here because I have to fill at least 1 in all 3 of these, the 2px, y, and z, before I add a second one to it. Okay? So let's look at oxygen. Now I'm going to cheat, and I've already started it. So oxygen has 8 electrons because it has 8 protons if it's neutral. So what I'm going to do is, instead of me filling it all, writing it all over again, I know from looking at this that my oxygen has 8 electrons. So I've represented 2, 4, 5, 6 here. I need to add 2 more to make the electron configuration for oxygen. So I'm going to add 1 more to the Z. Why didn't I put in the X or the Y? Because I have to have at least 1 of those before I add a second one. But now I have 1 in each. So now what I can do is I can add another one to one of these. So I'm going to put it here in the X. So now I have 2, 4, 6, 7, 8 electrons. Okay? All right. So I've represented both carbon and oxygen. Now phosphorus is 15. All right, I'm going to erase this because I don't have enough room. So I'm going to take this, erase this. I'm going to have to start over again. Okay, so I'm going to write here 1s, my next one, 2s, and then if you look after 2s, we do 2p. So we said that there's 3 of them because it can hold 6 electrons. So 2px, 2py, and 2pz. And that can hold a maximum of 2, 4, 6, 8, 10. 10 is not going to be enough. So I got to go beyond the 2p. So let's fill these first. So we said phosphorus, which is the one we're doing now, has 15 electrons. So I'm going to put 1, 2 in the 1s, 1, 2 in the 2s, and I'm going to put 1 here, 1 here, 1 here, and now I can fill a second one. 1 here, 1 here, and 1 here. So now I've represented 2, 4, 6, 8, 10 electrons. I need to do 5 more. So I filled my 2p, and my next, if I look down here, is I have the 3s is my next one. So 3s, I'm going to add 2 electrons to this. Okay. So far I have 2, 4, 6, 8, 10, 12 electrons. I filled my 3s. I'm now going to go to the third row, and I'm going to do my 3p. So 3px, 3py, and 3pz. And I need to add 3 electrons. So I'm going to put 1, 2, 3. So that's so now I have represented here the electron configuration of phosphorus. Okay? So that's electron configuration. Now, a simpler one. Okay, so what I'm going to do is I'm going to represent carbon, oxygen, and phosphorus. So carbon will represent this way: 1s2. So the superscript over the s means that there's 2 electrons in it. So carbon has 6 electrons. I've represented 2 so far. So we said the next one after 1s is going to be the 2s. So I'm going to write 2s. And I'm going to put 2 electrons in there. So I got 4. I need to represent 2 more. So, and we said that the 2p is going to be what I'm going to fill next. So I'm going to put 2p here, but I only need to put 2 electrons there. And so that's as simple as it is. I'm going to put this as how I represent the electron configuration using this method. Now, if it's oxygen, right, so this is carbon, my oxygen will look similar. I'll put 1s2, 2s2, and then 3p, but instead of being 2, I'm going to put 4 here. Is it going to hold a maximum of 6? So I can put 4 in there. Now the phosphorus, I'm going to put 1s2, 2s2, 3p6, because I can fill that one. So I got 10. I need to represent 5 more. And we saw down here in our electron configuration that after we fill the 3p, and sorry, I should have said 2p. That was a mistake I made in both of those. All right, I should have done 2p. All right, 2p here. So this is going to be 2p. So I fill my 2p. After my 2p, I'm going to go 3s. Okay, so we have 2, 4, 10. I can fill my 3s. And then after my 3s, I'm going to put them in the 3p. But I only need to put 3 in the 3p. Okay, so that's my electron. I'm going to erase this. And so if we look at let's look at carbon, oxygen, and phosphorus. And with the neon as well to make it interesting. Okay, so what we're going to do, excuse me, is we're going to represent the atom's nucleus by using the element symbol. So carbon, which we said has 6 electrons, but we're not going to represent all 6 electrons in electron dot notation. We just represent the valence electrons. So carbon is in group 14. So if we look at that, we take 10 away from the group number for any group that's 13 or higher, and that would be the number of valence electrons. So carbon has 4 valence electrons. That's in group 14. Excuse me. We take 10 away from those, and it represents 4. So you got 4 valence electrons. We said phosphorus. Phosphorus is in group 15. So we take 10 away from that, it's 5. So we're going to have 5 valence electrons. Excuse me. Oxygen, that's in group 16. 10 from 16 is 6. So you're going to have 2, 3, 4, 5, 6 valence electrons. Let's do chlorine. Chlorine is in group 17. So it has 7 valence electrons. So you have 1, 2, 3, 4, 5, 6, 7. So the little dots represent the valence electrons. And then finally, let's do neon. Neon is in group 18. 10 from 18 is 8. So if you look at neon, it has 8 valence electrons. Okay? That's as simple as it is. That's how we represent the electron dot notation, is you're just using little dots that represent the valence electrons. Okay, and thank you. And during the live session, if you have questions, ask me. And if there's something particular you have questions about, I will make follow-up videos for that. Okay, thank you.